At this point, we've spent some time discussing basic star characteristics. So we should have some familiarity with things like stellar distances through parallax, and we also introduced the Cepheid variable concept. The magnitudes of stars, both intrinsic or absolute magnitude and apparent magnitude, where absolute magnitude is like luminosity, apparent magnitude is like flux through the inverse square law. We discuss color and classification of stars and how that's based on temperature, the temperature of the stars, so spectral classification, and binaries and masses and how they relate. So we are now ready to press forward into the birth and life of stars, and this is a huge arena which is not going to be that easy to cover. We're going to discuss such things as stellar nurseries, the interstellar medium, dust and gas clouds, the protostar to pre-main sequence, zero-age main sequence time, stages of star birth, nebula and OB associations, helium burning, the biggest and smallest stars, the Cepheid variables in more detail, red dwarfs, red giants, star cluster ages, binary mass transfer. So we have a large task before us, so I invite you to get comfortable and let's dive into these topics. So what is the stuff between the stars? Is it all just empty space? Nothing? Well, no, there is stuff between the stars. Known as the interstellar medium, there is gas and dust, and it's about 10% of the mass of the galaxy. It consists of lots of molecules, things like hydrogen molecules, carbon monoxide, carbon dioxide, water, ammonia, ethyl alcohol, and many others have been discovered. Helium is abundant, but it doesn't form molecules. Now, the reason molecules form is because it's very cool. A shell should probably say cold between the stars, so molecules can form without being broken apart. There's lots of molecular hydrogen. That's the most abundant molecule. But it's very difficult to detect because it's so cold. It doesn't produce emission lines. However, carbon monoxide has special emission characteristics even when it's cold, and it emits in the radio, and they can be relatively easily detected. And fortunately, when you detect carbon monoxide, you're also detecting the presence of hydrogen because there's about 10,000 hydrogen molecules for every carbon monoxide molecule. Here in the picture, we see the Orion constellation and the surrounding region, and all this nebulosity you see here is carbon monoxide emission. And since you see a lot of that, it also indicates that there's even that much more hydrogen gas. So there's a lot of gas and dust in the Orion Nebula, as indicated from the carbon monoxide. There's actually about 6,000 molecular clouds in the Milky Way, masses that range from about 10,000 to a million solar masses. So that's quite a bit of stuff. The diameters are typically about 50 to several hundred light years. Densities 100 to 100,000 hydrogen molecules per cubic centimeter. Take the tip of your finger. 100 to 100,000 hydrogen molecules in that little space. Now that seems like quite a bit. But actually, even though it's thousands of times denser than the rest of the surrounding interstellar medium, it's only about 1/4 of the density of the air we breathe. Now that's pretty incomprehensible. If you happen to find yourself floating out here in the gas clouds of the Orion Nebula, which has some significant densities in terms of the interstellar medium, you would have no concept that there's anything around you. For all you would know, it's completely empty space. But that's the constituency and the density of molecular clouds, and they will play an important role in our subsequent discussion. So we often talk about nebula. Well, what is a nebula? It's just basically a region of dust and gas, but we need to distinguish the different kinds of nebula that we can have. Regions amongst, between the stars in the galaxies. First of all, there is emission nebula, and I have the H2 next to that. The H2 just means that it's singly ionized hydrogen. Well, that means that the electron has been removed from the hydrogen. And then when that electron is recaptured, it emits light. So here's the Cocoon Nebula in Cygnus. It's an emission nebula. What makes it an emission nebula? Well, there's hot, bright stars, sometimes in the center, but not always. Sometimes there are other places within or outside of the nebula where you don't see it. The particular star that has the energy to illuminate this thing or cause those atoms to be ionized. So the bright, young, hot star does this. And then electrons, of course, are excited. They're kicked into higher energy states or ionized. And then on the downward transitions, they emit Balmer photons. In particular, the red photon of Balmer emission, the hydrogen alpha. And so we see the characteristic red glow. So that beautiful red glow of an emission nebula is from electron transitions in hydrogen. You'll also notice in this image that on the outskirts we have these dark regions where it's simply like a plume of smoke blocking the light from sources behind them. So that's seen here as well. And then we have reflection nebula. This is a phenomena that's the same as the blue sky that we see, where sunlight enters the atmosphere and the short wavelengths are preferentially scattered, absorbed and re-radiated. So the part of the sunlight that enters our eyes from the sky, not looking directly at the sun, but at a different angle, are the blue photons, the short wavelength photons. So that's why the sky is blue. And in the same way, stars that are in dust and gas clouds, if the starlight is not energetic enough, but yet at the same time quite powerful, it will be scattered by the gas cloud that the stars are going through, like the Pleiades here going through a gas and dust cloud that is not part of the nebula from which the stars came from in the first place. And so it's not energetic enough to ionize the atoms, but it will scatter off of them. So we do see the bluish tint of the gas cloud that is passing through. So that is a reflection nebula. And as I just indicated, the difference between emission and reflection nebula has to do with the energy of the photons. So here we see in these black body curves or Planck curves, a B-type star, which of course is a powerful star, is far below the energy level of the photons produced by an O-class star. So you need photons with very high energies, ultraviolet photons, to ionize the gas. So that's what's required. Finally, then we have dark nebula, and it's very simple. They're just very dense clouds that are dense enough that the light from behind them just simply can't pass through. So it's opaque to the objects that may exist behind them, producing these silhouette, interesting configurations like this Horsehead in Orion. You may have noticed I keep talking about gas and dust clouds. Well, the molecular clouds we're talking about are mostly gas, but they also contain dust grains. And so here's a dust grain, an interstellar grain of dust, half a micrometer. Now these things make up about 1% of the molecular cloud mass. So even though it's not predominant, it is nevertheless important. Now many of the dust grains are a lot smaller than this, maybe 100 times smaller, or even smaller than that. And they affect the clouds in a very particular way. Here we see Barnard 68, which is a dark nebula, and it's not the gateway to another dimension as it may look. And it also does not mean that there's nothing behind it in terms of other stars. But what you can notice is along the very edges, there's a little bit of reddening. So there's a little bit of interstellar reddening because of the dust grains. And the reason for that is the same reason that we discussed already, namely that when we have an object producing light, and as its photons pass through the gas and dust, in this place particularly the dust grains are selectively scattering the shorter wavelength photons. The blue photons are scattered. In the same way that a smoky atmosphere will also really make the sun look a lot redder because it accentuates the whole blue sky phenomena, the scattering of the short wavelength photons by the gases in the atmosphere. So the dust grains do that also, and so what the observer sees then is the enhanced or the reduced blue light, so it appears as though it's an enhanced red light, making the object, like the sun, look a lot more reddish orange. Now the other thing is of importance that infrared light will pass through this dust. And so what we show here is the same image of Barnard 68 except taken in the infrared. Longer wavelengths, they pass right on through, enabling the stars to be seen that are actually there. They've been there all along. So in summary, the two things we're talking about. The interstellar dust reddens the stars. That's called interstellar reddening. And in addition to that, the dust can be penetrated by infrared light. And that's a significant reason why we take images and do studies out in space in the infrared. A very fruitful region to investigate the various nebula is the Orion system. So here is a recent, high-resolution, very awesome composite image of Orion and the various associated nebula. If you look at Orion, you would probably never imagine there's this much richness contained in this region. Well, let's look at this particular region here in a little more detail. So we have the Great Nebula of Orion, the Horsehead Nebula. Let's look at that in a little more detail. So some of the more famous and well-known nebula in Orion. The Great Orion Nebula itself, it's an emission nebula. It is significantly controlled by 4 stars, the trapezium, very bright, young, energetic stars that are carving out this particular molecular cloud. New planetary systems being formed there. Running Man Nebula, it's a blue reflection nebula. There is a very bright star, the easternmost star in the belt of Orion, Alnitek, or Zeta Orionis. And in this same area, we have the Flame Nebula, emission, and of course the Horsehead Nebula, which is a dark nebula. So let's take a little more detailed look at the Horsehead Nebula arena here. So here we have the Horsehead Nebula, Barnard 33. Very rich, very eye-appealing region in Orion that has all the various nebula types represented. Up here is a very bright O-type star, Sigma Orionis, ionizing the hydrogen atoms so that we have this emission nebula behind the Horsehead itself. We have a blue reflection nebula here from a bright B star. We have the Flame Nebula, another emission nebula, and dark nebula, the Horsehead, and other regions that you can see. So this is a good example of the various types of nebula that can all be strewn together right next to each other and all produced from various processes that we've discussed.